Okay, so this is kind of a complicated statement. I'll illustrate with some examples, and maybe you'll see it illustrated some more in the homework. Okay, so let's do some examples to try to make this clear. And we'll just go through all the possible dimensions, like 1, 2, 3, 4, 5, etc. So we'll start with dimension 1. It's a great dimension. Let's think about d equals 1. So what are the linear transformations that don't, in one dimension, that don't change lengths? There's basically doing nothing, and there's negation. That's like reflections. And that kind of makes sense because, R has to be 0 in this case because you don't even have enough dimensions to have like a two-dimensional plane of rotation. So then, you're just down to this case. In the remaining one direction, use either negation or nothing. Okay, that was not too surprising. Okay, let's go to d equals 2. And already there's a lot some going on in this case. So really what this is going to tell us about is every possible real unitary transformation in 2 dimensions. And there's a bunch of cases. So we can kind of case on what is the value of r. So one possibility is r equals 1. There's one two-dimensional plane of rotation. Okay, and that's everything. So that would mean P1 is all of the two-dimensional plane. And in that case, you're just acting like rotation by some angle, which is not 0 or 180 degrees. Okay, that's one kind of transformation in unitary transformation in two-dimensional space. And that kind of takes care of the r equals 1 possibility. So then we can go down to the r equals 2 possibility, r equals 0 possibility. So that kind of means r is 0, so we look at the 2 leftover dimensions. And each of these 2 leftover dimensions, the transformation can either be doing a negation or it can be doing nothing. So one possibility is that it's doing negation in both dimensions. So maybe I can reuse this picture. It's negating along the x-axis and negating along the y-axis. And that just means it's negating everything. So it's the negation transformation. So this is just u of a vector is negative the vector, which is also rotation by 180 degrees, by the way. And then another possibility is that it's negation in one dimension or axis, and it's do nothing in the other perpendicular dimension or axis. Okay? And so really this means that there's some one-dimensional subspace, if you will, one-dimensional line, where along this direction, u is negating. And then there's an orthogonal or perpendicular dimension along which u is doing nothing. And overall, what does this mean? Well, it means that, let's say you have some, wow, this is the curviest straight line I've ever drawn. Overall, it means if you have some vector, v, well, it's got some component in this direction, and it's got some component in this direction. And this direction gets negated, so it changes to, this thing gets negated, so it changes to this much. And this thing gets nothing, so it changes to nothing. It stays itself. And then the sum of these two things is here. So overall, this transformation moved this v to u v. So what kind of transformation is it? It's a reflection. It's a reflection through this line. Or it's a reflection kind of along this direction of negation. So this is a reflection maybe across the unnegated axis. Does that make sense? And then there's still more. The last case is like r equals 0, but in the remaining dimensions, they're all do nothing. So do nothing in all 2 dimensions. Okay, and this is just the literal unitary transformation that does nothing. This is the identity map that just leaves every vector itself. And so this is like the final categorization of all possible unitary transformations in 2 real dimensions. It's either a rotation by some amount that's not 0 or 180 degrees, or it's negation, which is kind of like rotation by 180 degrees, or it's a reflection, or it does nothing. Okay, so that kind of means that, by the way, that like there's no like, new kinds of 1-qubit operations that we haven't thought of yet. Like every 1-qubit operation, I mean, basically these 2 are the main cases. It's like a rotation or a reflection. And we saw some reflections like Hadamard and toggle, and I also told you like now I allow you to do rotation operations, so you can do it all. Okay, let's go up to 3 dimensions. I mean, Euler kind of more or less told us the story, but let's think about it. And already there's like enough cases that after a while I'm just going to be like, all right, I leave it to you to think about. But let's go through it for a bit. So how about d equals 3? Well, again, I mean, there's only 3 dimensions, so you only have space for at most 1 2-dimensional plane of rotation. That's kind of why Euler's theorem is true. You can't have something a higher dimensional. So if we categorize by r, then like one possibility is r is 1. And so then P1 is some 2-dimensional plane in 3 dimensions through the origin. And there's some rotation angle, theta 1, I guess, which is not 0 or 180 degrees. And, okay, so if you have a 2-dimensional plane, like slicing through that basketball, then there's like 1 dimension left, right, which is like the perpendicular line. That's the axis of rotation. That's the axis around which the 2-dimensional rotation happens. But actually, there's still possibilities, because we have this one remaining direction, and the transformation can either be negation in that direction or nothing. So if in the remaining direction, which is like the axis of rotation, we can either like do nothing, and that's just like that's like the regular rotation, or it can be negation. And if you like negate along this axis of rotation, it's kind of like you have to like, it can't be done in physical space. You've got to like turn the basketball inside out, so like it gets reflected through the plane of rotation, which maybe you can imagine, but like we can't actually physically do this easily in real life. So this is the main case. Like every unitary transformation in 3 dimensions is like a rotation in some plane plus optionally a reflection through that plane. By the way, we can't do a reflection through a plane in real life because we're stuck in 3 dimensions. But if we had a 4th dimension, then we could execute that reflection by a rotation. Maybe you don't know what I'm talking about, but it's the same way that like in real life, if you have this piece of paper and you want to like reflect it, like imagine this is kind of transparent. You can use the 3rd dimension to reflect it, you know. So it's like a rotation, a reflection in 2 dimensions can be accomplished by a rotation in 3 dimensions. And actually, I realized at some point that's why like 2 reflections equals a rotation. If I take this paper and I reflect it once, I can accomplish that with a 3D rotation. And then I reflect it again along some other axis. I do another 3D rotation. You kind of see that like I've overall not reflected it, but the only possibility left is that I rotated it. Anyway, that's like a callback to the previous lecture. Yeah, so this is the main case in 3 dimensions. And all the remaining cases, you have to go through them a little bit, like our r equals 0 cases. That means there's no rotation, but there's still 3 remaining directions along which you could have optionally negation or not negation. So the remaining possibilities are rotation by 180 degrees within some 2D plane. So like there's some 2D plane in which you negate, but like you don't negate in the third remaining direction. Or reflection across some 2D plane, but no rotation. Or you just negate everything. U maps a vector to its negation. Or nothing. Like every vector stays the same. So those are all the 3D possibilities. Now I want to connect this back to quantum computation. And you might say that's like a little bit difficult because, you know, in order to get at least 3 dimensions, we need to go to 4 dimensions by having 2 qubits. But I'm going to give you an example that is fundamentally 3-dimensional. So here's a quantum example. Remember way back on like homework, I want to say 1, we considered this 2-qubit operation, which I called increment mod 3. So this was about like incrementing a number mod 3 in base 2. So what that meant was like the definition of the operation was that like 0, 0, which is supposed to represent the number 0, goes to 0, 1. And then that's 1. And then like 1 goes to 2. And then 2, it's supposed to be mod 3. So when you increment, it goes back to 0. And then 4, you're like, we're not trying to use 4. So like, we got to send it somewhere, but we'll just like leave it at itself. Okay, 4 goes to 4, technically. So this is some kind of, this is a 4-dimensional unitary. So it's some kind of rotation and reflection in 4 dimensions. Remember, by the way, like, what does this mean? This really literally means the vector 0, 0, 1, 0. And this literally means the vector 1, 0, 0, 0. Yeah, so this is some kind of 4-dimensional rotation or reflection, and let's try to understand what's going on. And you know, one thing we can say is there's one direction, this 4th dimension, where like nothing happens. Like this increment 3 is acting as like a do nothing in this direction. So we can basically forget about it. Like there's some 4th dimension where like nothing changes. So we'll just like forget about that dimension so that we can think about a 3-dimensional example. And yeah, this sort of transformation is a unitary transformation in 3 dimensions. And so we'll think about the sense in which it's a rotation or a reflection. Okay, so this is increment mod 3, or another way to write it is if you have like x amplitude on 0, 0, and y amplitude on 0, 1, and z amplitude on 1, 0, which, by the way, that's like x, y, z, then what happens? Well, this 0, 0 goes to 0, 1, and this goes to this, and this goes to this, so it goes to x 0, 1 plus y 1, 0 plus z 0, 0, which is this, y, x, z. Okay, so this is how the increment mod 3 operation acts. It takes this kind of vector to this kind of vector. Actually cyclically shifts their coordinates. So this is a transformation on 3-dimensional space. Yep. Yeah, so technically, the way this transformation actually works is you have like plus w 1, 1, and it goes to also plus w 1, 1. So this technically needs a 4th dimension w, and this needs a 4th dimension w. But somehow, like for every value of w, like I don't know, 0.2, you stay within the 3-dimensional sort of space where w is fixed to 0.2. So like all the action is always happening sort of in the x, y, and z directions. Nothing is happening in this 4th dimension. So for the purposes of illustration, because like 3 is the last dimension we can visualize, I'm like, let's just ignore that dimension. Yeah. Okay. Or if I was just like, well, forget quantum and just we'll talk linear algebra, like consider this linear transformation on 3 dimensions that maps these vectors to this vectors. So apparently this is a rotation. Can you visualize it? Let's try to do it. I need the basketball for this. Oh, thank you. Yeah, I'm ready. Perfect, chess pass. Okay, so this is the ball in 3 dimensions. So let's take this. Okay, so we need to, what I want to do is I want to identify these 3 vectors. Right, so I want to identify 0, 0, that's like 1, 0, 0. And maybe I can do it with colors. 0, 1, that's like 0, 1, 0. And 1, 1, 0, that's like 0, 0, 1. Okay, you should really think of this like a globe. I was going to bring in a globe of the Earth, but then it cannot freely rotate a globe, so I didn't. But let's see. So let's pick on the globe, like straight up. Let's orient it like this. So 0, 0, 1, that's like the z-axis. Let's straight up. So let's mark that here. Okay, that's like, you can't see it, but anyway, this is the North Pole. So that's like 0, 0, 1. And then we need like, let's say 1, 0, 0. That's like on the equator. That's like you come from the center of the ball out to, let's say, here. If this were a globe, this would be like Western Africa. So let's say Gabon. Remember Gabon, right? Season 17 of Survivor. A physics teacher won that episode, or season. Okay, and the last thing, it's going to be like also in the equator. Like it's at height z equals 0, but it's like in the orthogonal direction. So that's like 90 degrees away here. So that's like Singapore. Also on the equator, but 90 degrees away from Gabon. So we have like North Pole and like Singapore and like Gabon. And like Gabon goes to Singapore, Singapore goes to the North Pole goes to Gabon. Right? So this is a rotation, right? It's a rotation through like this axis right through the middle of the triangle, like right through. I think this is like Iran here. So actually this, it doesn't look like it, right? I mean, at first, this transformation, it looks like it's just mixing around the coordinates, but it is like visually, I mean, you can see it's actually a 2-dimensional rotation. Do you know what that rotation angle is? I'll somehow show it to you. Again. Where is it? Here it is. How much did I rotate it by? Yeah? No? I mean, maybe I can draw it. Like, maybe it's easier if I, like, somehow, like, here it is. Here's the globe. Like, here's the North Pole up here. Like, here's, like, Gabon down here. And here's, like, Singapore is, like, down here. And, like, this is going here, this is going here, this is going here. Yeah? 120. Yeah, it's a third of a full turn. It's 120 degrees. Here's Tehran right here. This is 120 degrees. It kind of has to be 120, right? Because we know if you do it 3 times in a row, okay, I can't illustrate it. If you do it 3 times in a row, you get back to where you started, right? If you do this transformation, this like cyclic shift transformation 3 times, that's how you get back to where you started. So the only rotation angle that has this property is 120 degrees. Okay, so indeed, in summary, this increment mod 3 operation is a rotation. It's rotation by 120 degrees around the axis that goes through Tehran, or the midpoint of these 3 vectors. I mean, the axis points in the direction 1, 1, 1, actually. Okay, so on your homework, you will do the same story, but for increment mod 4, which is a genuinely 4-dimensional transformation. And you will try to understand in what sense it's a rotation in 4 dimensions. And like, are there 2 P's? Now there's room for 2 planes of rotation. So are there 2 of them? Or is there 1 of them? Or is there 0 of them? What are the rotation angles? You'll find out. But as a clue, you should remember, if you do increment 4 times in a row, it corresponds to doing nothing.